Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our discussion of correlation and regression, and we're going to be focusing on that last component that we wanted to measure and understand when looking at the relationship between two quantitative variables, namely the strength of the relationship. If you remember from the previous video, we saw that by making use of the visual display, the scatter plot, we can have a pretty good sense of the direction and the form of the relationship, or lack thereof, between two quantitative variables. But strength was something harder to do visually. So in this video, we're going to introduce a way of measuring the strength. So the way we're going to be measuring the strength in our class is what is called the correlation coefficient. So the definition, the correlation coefficient, which is denoted using the letter R, measures the strength of the linear correlation between two quantitative variables. So the key thing to sort of keep in mind here is that the correlation coefficient, first of all, its variable name is R, so the letter we'll be using is R, and the second thing is that it measures the strength of a particular type of correlation, linear correlation. So the correlation coefficient tells us about the linear correlation between the two quantitative variables. And that's very important. For our class, we're going to be pretty much focused only on understanding linear relationships, but as we saw, it's not the only type of relationship out there. There's exponential and nonlinear, so we do need to be careful and understand that the correlation coefficient, while great for linear relationships, is limited to linear relationships. All right, let's talk about a couple quick properties of the correlation coefficient and then talk about how we're going to actually calculate it. So the first property of the correlation coefficient is that when you calculate it, you're always going to get a value between -1 and 1. So correlation coefficients are always decimal values between -1 and 1. The way we understand the correlation coefficient is that the closer R is to either positive or -1, the stronger the linear correlation between the two variables. The closer the correlation coefficient is to 0, the weaker the linear correlation is between the two variables. So if you want to visualize that as sort of a number line, what you can sort of imagine is if we have our number line there, if that is -1, and that is +1, and right in the middle is 0. Well, what this is telling us is that this stuff over here is strong positive correlation. This stuff over here near -1 is strong negative correlation. So you can see that the correlation coefficient also tells us not only about strength, but also about the direction. A negative correlation coefficient is telling us we're seeing something that's negatively directed. A positive correlation coefficient is telling us that we're seeing something that is positively directed. Here, we're seeing this would be, as we get closer to 0, weak negative correlation. And here, this would be weak positive correlation. A couple quick notes to here. If we ever get R equals ±1, which of course isn't going to really happen for real data, but just to understand what that means. So if you end up at one of these two ends, then what this means is this tells us that we're looking at perfectly linear data, meaning that if we were actually to draw like a scatter plot and get an R of ±1, it means that the points don't sort of generally form a line, they literally form a straight line where every point is on there. When we get very close to 0, when we get R equals approximately 0, that means no linear relationship. Now, you'll notice that I am being very careful about specifying no linear relationship. The reason that the correlation coefficient, or one of the reasons that the correlation coefficient by itself is not sufficient, why we still want to make use of things like scatter plots, is that if you had a scatter plot that looked like this, where there is no relation, you would get R approximately 0. If you had a relationship like this, there is definitely a relationship, but you would still get R is approximately 0. Why? Because that second one is non-linear, right? If you see something like this, I mean, there's a pattern, but it's not a linear pattern. So both of those pictures will yield R is approximately 0, so we have to be very careful. R being approximately 0 doesn't mean that there's no relationship overall. It means there's no linear relationship. Okay, so you can see that this is really the main sense of this measure. This measure, the closer it is to -1 or 1, the stronger our correlation. The closer to 0, the weaker. Now, you might say, what if we land in between, like somewhere between 0 and -1, right? Or it's between 0 and 1, somewhere medium. How do we decide if it's strong enough? Well, we'll talk about that in just a moment. We're going to make use of a statistical table that'll tell us how strong is strong enough. But for now, let's talk about a couple other properties. Property 2 here, R is unitless. All this means is that, 1, is that when you write out correlation coefficients, you don't put any units on them. And 2, when you change the units of how you measure the explanatory response variables, that does not change R. All that means is, say you're trying to understand the relationship between height and weight. Well, if you measure your heights in inches and your weights in pounds, you will get the same correlation coefficient as if you decide to remeasure everybody with their heights in centimeters and their weights in kilograms. It won't impact anything about the pattern. The pattern is not dependent on how you decide to measure the explanatory or response variables. Fact 3 is actually a pretty shocking one. R is symmetric. What this means is that if you were to accidentally interchange the explanatory and response, so you accidentally identify the explanatory as the response and the response as the explanatory, this does not change R. Now you might say to yourself, well, then why did we make such a big deal about correctly identifying explanatory and response? 2 reasons. One is fundamentally to understand a relationship, we need to know which one is explanatory and which one is response. Even though R might not change values, the way we understand the relationship would change based on which is explanatory and which is response. The second reason is that as we move forward into regression, which is basically where we'll be building models and equations based on the data, then it is very dependent on which is explanatory and which is response. So we have to be very careful about it. So yes, your R value will not change if you accidentally reverse which one is explanatory and which was response, but a lot of the interpretive stuff will get thrown off by that. So while R is symmetric, you need to still be careful about making sure you get the correct explanatory and the correct response. Finally, R is not resistant. Remember, back when we first started introducing statistical measures with mean and median and things like that, we talked about how every statistical measure should be thought about as whether or not it's resistant or not resistant. Well, it turns out that R is based off of the mean and standard deviation. Behind the scenes, in terms of calculating a correlation coefficient, is based around calculating means and standard deviations. As we know, means and standard deviations are not resistant. So R is not resistant. This means that extreme values can significantly impact R. We'll see this much later on at the very end of our discussion of correlation and regression. We'll look at some examples of how extreme data points can really impact the correlation coefficient. Okay, let's talk a little bit now, since we have these properties about how we're actually going to calculate it and use it. So, using the correlation coefficient. We're mostly going to use the correlation coefficient in our class to decide if there's enough evidence for a correlation or relationship between two variables. In other words, we're going to use the correlation coefficient to mathematically decide, is the pattern that we're seeing in the data strong enough to really be viewed as a pattern, or does it just happen to still be a random jumble? This will be really important because if we can use the correlation coefficient to truly establish that there is a pattern, then we can model that pattern and use that pattern to make predictions, draw conclusions, etc. So, how do we actually use the correlation coefficient? Well, we will do that by also making use of another statistical table. This is statistical table E. You can find this in the document of statistical tables, same place that you found statistical table A. Now we will want to make use of statistical table E. To use table E, you need to know only one thing, the sample size n. Let's go take a look at what table E looks like and talk about how to use it. So, this is what table E looks like. It's called the critical values of the correlation R. So you notice it says right in its title that it's related to correlation R. The first column is n, which is your sample size, so you need to know how big your sample is. Once you know that, you'll locate that on this column. So maybe you have a sample of size 10, so you locate yourself right there. Then you will notice that I've circled the 0.025 column. This is the column we're always going to use in here. It's a little bit beyond where we're currently at in our class to talk about why on this table there's so many different options. We will only be using this one. As a quick explanation, what this 0.025 represents is that we are willing to accept a 0.025 or 2.5% chance of accidentally saying that there is a correlation between two variables or there is a relationship between two variables when there really is not. We'll be able to discuss that more later when we get into hypothesis testing much further on in our course, but for now just realize we're always going to use this column. So what you will do is you would intersect your sample size along here with this, and this value in the table is what is called the critical value. It basically tells us what the cutoff is for what counts as strong enough. All right, we'll do an example of that in just a moment, so let's just make a note of how we read table A. We find our n, which again is our sample size, and we always use that 0.025 column. We go across, and when we intersect those, we find what is called the critical value inside the table. So how do you use the critical value? Well, if your correlation coefficient is greater than the critical value, now you'll notice that I'm putting the correlation coefficient in absolute value. Absolute value just means that regardless of whether or not the R is positive or negative, you treat it as a positive. That's just to make the comparison fair, because comparing negative numbers to positive numbers isn't really measuring the size, it's just measuring positive or negative. So we'll always do it in absolute value. If the absolute value of your correlation coefficient is larger than your critical value, then this tells us that we have enough evidence for a correlation or for a relationship. If the absolute value of your correlation coefficient is smaller than your critical value, then this tells us that there's not enough evidence for a correlation or for a relationship. In other words, the pattern is not strong enough to really be considered a true pattern. All right, as a final note here, you might be asking yourself, how do we actually calculate this correlation coefficient? Now we know how we're going to use it, but how do we actually get it? Well, we will be calculating the correlation coefficient exclusively through the calculator. There is a separate video for how to make use of a TI brand calculator and calculate the correlation coefficient. I would recommend pausing this video now, watching that one. It's very short, it's only about 5-10 minutes. Watch that and then come back to this video to finish up the last example where we will actually take some data and calculate this correlation coefficient and use it to diagnose if we have enough evidence. So if you haven't watched the calculator demo video, go ahead, pause this one and watch that now. Otherwise, let's get to that example. So for this example, we're going to suppose that we are interested in studying the relationship between the budget and revenue for blockbuster films. So to do this, you collect the data about 12 recent blockbuster films. You record the budget of each film in millions of dollars, so their budget is in millions of dollars, and then their revenue also in millions of dollars. And you get the following data. So here's our data here. So just since this is real data, just so you guys sort of know, this first film here, which had a budget of $400 million and a revenue of $860 million, this was actually Avengers Endgame. And then also, just because I think it's interesting, this is one of the worst flops in movie history. A movie with a budget of $260 million that only managed to make $70 million in revenue. If you're at all aware of like how the movie industry sort of works, making a revenue, generally, it's not even a success until you've made double your budget. So something like Avengers Endgame, yes, I mean, huge release, but it's just barely, in terms of monetary making, in terms of the money that the movie took in, barely a success because it only just made it over double its budget. Something like this that actually made less revenue than their budget is a total flop and disaster. This movie right here, this was a movie called John Carter, which I believe was by Disney. It's based off of a novel. A complete flop, one of the biggest flops in sort of Hollywood history there. All right, so we've got all these movies with their budgets in millions of dollars and their revenues in millions of dollars. Let's go ahead and do a couple things with this. First, we're going to do our standard starting process, which is identifying the explanatory and response. Again, this one should be very clear based on the chronology, right? The budget is set first before the revenue, so we know that the budget should be the explanatory variable and the revenue should be the response variable. The budget, if there is a relationship, might help us understand how much money it makes. It might not, but it doesn't make any sense to say that the revenue impacts the budget. Now, since you've watched the calculator demo video, you'll know that in terms of our calculator, we'll want to put the explanatory variable into L1 and the response variable into L2. So if you have your calculator and you're trying to follow along here, go ahead and hit Stat, Edit. In L1, go ahead and put those budgets, so 400, 380, 370, 310, 300, 300 again, 300 again, 300 again, 280, 270, 260, and 260. Then go into L2, clear out any data that might already be in L2, and go ahead and put in the revenues, 860, 240, 460, 940, 310, 200, 680, 230, 520, 210, 70, and 330. Make sure, again, all those are paired up. So your first one should be 400 in L1 and 860 in L2. The next one should be 380 and 240. It's important that the pairs are maintained here. Okay, so we'll need that a little bit later on. For now, though, we've identified the explanatory and response, so that's part A right there. Let's go ahead and get ourselves a scatter plot for this. We can do that right here. So since we said budget should be the explanatory variable, that means budget needs to go here. And remember, this is in millions of dollars. And this should be the revenue, also in millions of dollars. So let's figure out what sort of scales look good for budgets. It looks like the lowest budget was 260 and the highest was 400. So we could, again, start with anything you sort of like. Maybe we'll start with 250 and go by 50s. So there's 250, 300, 350, and 400. And of course, we'd have to put a little squiggly line to show that that's been condensed. So the highest budget was 400. Okay, good. For revenues, it looks like they're a bit more split out. The lowest revenue was 70 all the way up to 860. We can just go by hundreds, I suppose. So 100, 200, 300, 400, 500, 600, 700, 800, and 900. So there we go. Notice that on the vertical axis here, we will not need any sort of little squiggly line. This has not been condensed. This really would be 0 in terms of the vertical axis this time because we went 0, 100, 200, 300, etc. Okay, let's plot these points. First one was 400 and 860. So 400 and 860 should give us a point right about there. Then we had 380 and 240. So 380 and 240 gives us a point probably right about there. Okay. Then we had 370 and 460. So 370 and 460 looks like maybe right about there. Okay. Then we had 310 and 940. Oh, I missaw it. There's the highest revenue, so we actually need to go one more up to 1,000. My apologies there. So we had 310 and 940. So 310 and 940, that is way up there. Okay. Then we had 300 and 310. So 300 and 310, something right about there. Then we had 300 and 200, so that would put us right there. Then we also had 300 and 680, so that would be right about there. And then we also had 300 and 230. So that should be right about there. Okay. And then we had 280 and 520. 280 and 520. Looks like that should be right about there. Then we had 270 and 210. 270 and 210, so it looks like right about there. Then we also had 260 and 70. So 260 and 70. Looks like that would be right about there. And then we also had 260 and 330. So 260 and 330. Maybe a little bit more over. Probably right about there. All right, so there we go. There's our scatter plot. Points seem to be all over the place. If we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, 12 points, 12 movies in our sample. There we go. So there's our part B there. All right, now, before we go and calculate the correlation coefficient, I mean, what sort of pattern are we seeing here? Well, it's hard to sort of tell. It seems like the points are sort of scattered everywhere. If we were to make a guess, though, it seems it doesn't really make sense to go like that. It seems more, if anything, like this. So we're expecting maybe a positive correlation of some sort. It's certainly a positive correlation coefficient, but is it going to be enough to really say that there's evidence of a relation? Well, this doesn't seem like a strong pattern, so we'll have to see. So to actually calculate the correlation coefficient, remember we're going to hit stat, calc, lin, reg, ax plus b. Remember, again, if you haven't watched the calculator demo video, I highly recommend going back and doing that first before doing this. That does do an example of typing the data in and using the calculator to calculate the correlation coefficient. If you have watched that and you have your data in L1 and L2 from above, you hit stat, calc, lin reg ax plus b. Make sure that you have L1 and L2 as your list there, or if you have the older calculator, it's defaulted to that. If you do have a newer calculator, make sure the frequency list is blank, and then you can go ahead and hit calculate, and we should find an R here of approximately 0.4124. We usually keep 4 decimal places for correlation coefficients because that's also what we get for critical values. So there we go. There is our correlation coefficient. Notice it is positive, as expected. We sort of are seeing positively directed. Is it going to be strong enough? Well, we have to actually go ahead and decide. So let's go ahead and take a look at our critical value. So we'll go to table E now. And table E. And remember, we have n equals 12. We have 12 data points, so let's go take a look. So for this one, we can go ahead and find n equals 12. Remember, we always go ahead and use this. So if we intersect this and this here, well, that means our critical value is going to be that 0.5760. What does this critical value mean? Again, remember, it means the cutoff. Notice that in this column, for very small amounts of data points, you have very high cutoffs, right? If you only have very little data, you need a very strong pattern before you're convinced to say it really is a pattern. The critical values get smaller and smaller as you go further down, because if you have tons of data, if you have like 1,000 data points, you only need a very weak pattern to say, well, I still believe there's a pattern because I have so much data. So the more data there is, the smaller the critical value, because we're willing to accept a weaker pattern based on the fact that we have more data. In this case, we had 12 data points, so there's our critical value, 0.5760. So let's go ahead and write that down. Our critical value was equal to 0.5760. How does this R value compare to that critical value? Well, as we can see in this situation, the absolute value of R, which is unnecessary because R is positive, but just good habit, is actually less than the critical value. 0.4124 is smaller than 0.5760. So we would have to say there's no evidence for a relationship or correlation. In other words, from our data, we are not convinced that the budget has an impact on the revenue for blockbuster films. We saw some that had small budgets and did quite well. We saw some that had high budgets and didn't do as well. So we're not convinced that there's a relationship between these two variables. All right, so this gives us now sort of a wrap up to our introduction with correlation. We know how to visualize the data that we're looking at, and now we know how to measure the strength and make a decision about whether or not variables are actually related. The next natural question, of course, is if we do find out that the two variables are related, what more can we do with that? And we'll explore that in our next video.